Hi friends, today we are going to discuss about two new concepts, one being electrostatic potential energy, which is being designated as U, and then electric potential, a very important concept in the field of electrostatics and called as V. So let's first try to understand what electrostatic potential energy is. Let us consider a charge Q1 positively charged. This is present in space. Let us assume that there are no charges present in its vicinity. Let us now consider another charge Q2. Once again, this is positive, and this charge Q2 is present at this point P. Let the distance of separation between these two charges, let it be R. Now try to understand. Q1 is positive and Q2 is also positive. So there is going to be a lot of repulsion between these two charges in accordance with the Coulomb's inverse square law. Like charges do repel. Now one has to do a lot of work in placing this charge Q2 at this point P, because that particular external agent who is doing this work, he or she should face a lot of repulsion. Let us imagine that this Q2 was brought from infinity by a person, and this particular person, let's call Mr. Small x. He's a very nice guy, he's a smart guy. So what he has done is, he has done a tremendous job in lifting this particular charge Q2 from infinity, and he has put this particular charge at this point P. Great job, Mr. X. Now let us assume for a moment that X is taking rest at this point, and let us call this point as A. At A, Mr. X is now taking a lot of rest. Now at A, what happens in the sense, there is this repulsive force, which is F electric, which is acting along this direction, and Mr. X has to overcome this repulsive force. So he has to move forward in this direction. So this is the direction in which Mr. X has to apply this force, which is Fx. Now the work done by Mr. X in moving this charge from infinite or infinity to this point P, can it be calculated? Yes, of course, it can be quantitatively described. Let us assume that the distance between this first charge Q1 and the point A is small r. Now let us calculate the work done by Mr. X. So the work done by Mr. X, let that be W suffix x. So that's nothing but, the work done is nothing but moving this charge from infinity to this particular point R. So we can take the limits of the integral as infinity, the lower limit, and the upper limit as R. And the work done is always force into displacement. Thankfully, the X is moving in the direction of dr, so that's good news. So he is doing tremendous amount of work in marching towards the point P. Now we need to calculate and evaluate this integral. So what we do is, we slightly swap the forces if you look at this cartoon, you will understand that the electric force of repulsion and the force executed by Mr. X are one and the same, and they are oppositely directed. Now, instead of calculating this force Fx, what we are going to do is, it's easy for us to calculate this force electric. So let's calculate this force, and the electric force and the direction of displacement is also in the same direction. So instead of infinity to r, we take this as r to infinity, because electric force is directed from r to infinity. That's the force of repulsion. Now it's easy for us to do this integral. Why? Because we know the value of Fl, which is given by Coulomb's inverse square law. So which is nothing but Q1 Q2 divided by 4 pi epsilon 0 and integral dr by r square. So let's complete this process, and if you integrate this, we'll be getting Q1 Q2 4 pi epsilon 0. So 1 by r square, the integration is minus 1 over r. So the upper limit being at infinity and the lower limit is r. So if we evaluate this integral, so we can get the work done, which is Wx as Q1 Q2 by 4 pi epsilon 0 capital R. 1 by infinity is always 0. Minus of minus 1 by r is plus 1 by r. So we have evaluated this integral. Now the work done by Mr. X in bringing the charge from infinity to the point P is stored as the electrostatic potential energy U. So U is equivalent to Wx, which is equal to Q1 Q2 by 4 pi epsilon 0 r. So electrostatic potential energy U is Q1 Q2 by 4 pi epsilon 0 r, the unit being J. Now U is a scalar quantity, which implies that U can be 0, it can be greater than 0, greater than 0, it can be lesser than 0. It's a scalar quantity. Now using this concept, let's discuss our next topic, which is electric potential. Let's take a big charge, mighty charge, and let's call this as mighty charge as Q. Once again, for the sake of convenience, we will assume that this charge is positively charged. Let's take a very small charge, which is our test charge. Let's call this as Q0. Let us assume that this Q and Q0 are separated by r, by a distance r. Now you know that the work done in bringing this charge, test charge Q0 from infinity to this point P is nothing but the electrostatic potential energy we have just now studied. So let's state the electrostatic potential energy here. So in this context, it is going to be Q0 over 4 pi epsilon 0 r. Now let's try to define what electric potential is. So electric potential at this point P can be defined as work done per unit charge. Now let us write this in a proper way, in a mathematical way. So Vp is going to be U over Q naught. Now we already know the value of U, so it's Q naught over 4 pi epsilon 0 r, and if you include this Q naught per unit charge, this test charge will disappear. So what we get here as a relation is going to be Q by 4 pi epsilon 0 r. Now this is the expression for the electric potential, Q over 4 pi epsilon 0 r. Now the unit for electric potential is Joule over Coulomb, but nobody uses this particular unit, so it is always expressed as volt after the great scientist Volta. Once again, this electric potential is a scalar quantity. It is a scalar, so it can be positive. Electric potential can be negative, and we have certain areas where it can have zero value. The potential can be zero. Remember, electric field is a vector quantity. However, electric potential is a scalar quantity. So in these three lectures, we have discussed three important concepts. So let's revise those concepts. The first concept being the Coulomb's inverse square law. So the force between two charges can be expressed as the product of the magnitude of the two charges Q1 by Q2, the whole divided by 4 pi epsilon naught r square, and this is r cap is used to indicate the direction, so this is Coulomb's law in vector form. In the last video we discussed what electric field is. So electric field is K is nothing but 1 by 4 pi epsilon naught. I am deliberately writing interchangeably. I am swapping between K and 4 pi epsilon naught to make your understanding that much more clearer. KQ divided by R square. Then now in this class we have studied what is V. So V is nothing but KQ over R. So these are the three concepts what we have learned so far. So once again, electric field is a vector, so we can put this unit vector symbol r cap. In the next lecture we shall see the relationship between these two quantities, electric field and electric potential, and that's going to be the agenda for our next class. Until then, goodbye.